Right now, Voyager 1 is roughly 15 billion miles from Earth, drifting through interstellar space at about 38,000 miles per hour, carrying a golden record nobody has ever played. That part of the story you probably already know. What's genuinely strange is that astronomers have actually run the physics forward, not just for the next few decades, but for trillions of years, to figure out where this one small machine is likely to end up long after Earth, the Sun, and everything currently alive has become ancient history. To be clear about where things stand today, before jumping forward in time, Voyager 1, launched in September 1977, crossed into interstellar space in August 2012, and is still functioning in a limited way, nearly 49 years later, running on a slowly decaying plutonium power source that NASA's engineers have been carefully managing for decades, switching off one instrument after another to stretch the spacecraft's remaining electricity as far as it will go. Even in a best-case scenario, Voyager 1's instruments and radio transmitter are expected to fall permanently silent sometime in the early 2030s, once its dwindling power supply simply can't sustain any operations at all anymore. That's the part of the story with a knowable, relatively near-term ending. What happens after that, after the spacecraft goes quiet and simply becomes a drifting, inert object, is a completely different kind of question, and it's the one this video is actually built around. This is what that math actually says, using real published research, not speculation. Let's start with the person who ran the numbers. Nick Oberg, a doctoral candidate at the Kaptein Astronomical Institute in the Netherlands, along with a colleague, set out to answer a fairly narrow practical question. Using detailed new star position data from the European Space Agency's Gaia spacecraft, which star, if any, might Voyager 1 or Voyager 2 pass anywhere near in the future? Oberg presented the results of that work at the 237th meeting of the American Astronomical Society, and what started as a modest exercise in stellar cartography ended up producing a forecast stretching billions upon trillions of years into the future. A forecast that outlasts not just human civilization, but the sun itself, and even most of the stars currently burning in the night sky. The reason Gaia's data mattered so much to this particular question is worth explaining briefly, because it's what made this level of precision possible in the first place. Gaia is a European Space Agency spacecraft specifically designed to map the positions, distances, and motions of more than 1 billion stars across the galaxy with extraordinary precision, far beyond what any previous star catalog could offer. Before Gaia's second major data release, astronomers simply didn't have precise enough measurements of how nearby stars are actually moving through the galaxy to confidently project which ones might drift near a specific, slow-moving spacecraft tens of thousands of years from now. Oberg's research was essentially the first serious opportunity to ask that exact question with real confidence, once that new, far more precise stellar motion data became available to work with. Before we get to the truly enormous timescales, it's worth walking through the nearer-term milestones first, because even those are stranger and slower than most people assume. Voyager 1. Voyager 1 already crossed the heliopause, the boundary of the sun's influence, back in August 2012, technically entering interstellar space. But according to Oberg's modeling, that's not actually the moment the spacecraft leaves the solar system in any meaningful gravitational sense. The sun's gravity and the Oort Cloud, an enormous distant shell of icy debris that extends up to 100,000 times the distance between the Earth and the Sun, still surrounds Voyager 1 for a long time yet. Oberg's research places Voyager 1's crossing of the outer edge of the Oort Cloud at roughly 20,000 to 30,000 years from now. That's the point, he noted, at which the spacecraft will finally begin feeling the gravitational pull of other stars more strongly than it feels the sun's, the real physical moment it stops belonging, gravitationally, to our solar system at all. It's genuinely worth sitting with how strange that distinction is, because it means Voyager 1 isn't actually leaving the solar system right now, in any complete sense, despite the interstellar space headlines from 2012. The heliopause marks where the sun's outward stream of charged particles, called the solar wind, finally gets overpowered by the pressure of the wider galaxy's own interstellar material, a boundary defined by plasma physics, not gravity. The Oort Cloud, by contrast, marks the outer limit of the sun's actual gravitational reach, the point where the sun's pull on a distant object finally becomes weaker than the pull of the galaxy and its neighboring stars. Voyager 1 crossed the first kind of boundary back in 2012. It won't cross the second, genuinely more complete kind of boundary for tens of thousands of years yet, meaning, in the strictest gravitational sense, the spacecraft is still, technically, inside the outer reaches of our own solar system today, and will remain so for longer than the entire span of recorded human civilization. Somewhere close to that same window, Voyager 1 is expected to pass relatively near another star for the first time. Different research groups have landed on slightly different candidates for exactly which star that will be, which is itself worth being upfront about. Earlier calculations, going back to the Voyager Golden Record documentation itself, pointed to a star called Gliese 445, currently sitting in the constellation Camelopardalis, with Voyager 1 passing within about 6 light years of it in roughly 40,000 years. Oberg's more recent modeling, built on the newer Gaia data, instead highlighted a red dwarf star called Ross 248 as the more likely close encounter, occurring around 30,000 to 40,000 years from now. As Oberg put it, it's a bit misleading to even call it a flyby in the traditional sense. From Voyager 1's perspective, it will be sitting nearly motionless, while Ross 248 itself is the one doing the moving, drifting past the slow, nearly stationary spacecraft. Either way, both estimates land in roughly the same tens of thousands of years range, and both illustrate the same basic point. Even a close stellar encounter for an interstellar spacecraft happens across a span of time longer than all of recorded human history combined, several times over. That discrepancy between the two estimates is worth pausing on briefly, because it's a good, honest example of how this kind of long-range forecasting actually improves over time rather than being fixed once and never revisited. The original Gliese 445 estimate dates back to calculations made around the time of the Voyager launch itself, using the comparatively limited stellar position and motion data available in the late 1970s. Oberg's Ross 248 estimate reflects a genuine scientific update, made possible specifically because the Gaia mission provided dramatically more precise measurements of how nearby stars are actually moving through the galaxy. Neither estimate is simply wrong. They're both reasonable calculations built on the best data available at the time each was made, and the gap between them is a useful reminder that even confident-sounding numbers in a video like this one rest on the quality of the underlying data, which keeps improving as better instruments like Gaia come online. Zoom out much further, and the story shifts from individual stars to the shape of the galaxy itself. According to Oberg's modeling, roughly 500 million years from now, both Voyager 1 and Voyager 2, still moving with the Sun's own orbital motion around the galactic center, will complete one full orbit around the Milky Way. The same journey our entire solar system takes roughly once every 225 to 250 million years. 500 million years, Oberg noted, is a timescale comparable to the formation and eventual breakup of an entire supercontinent here on Earth. Arguably the last time anyone can say anything at all confident about, because there's simply no way to predict what, if anything, will exist on Earth's surface by then. For comparison, 500 million years ago on Earth, complex animal life had only just begun colonizing land for the first time. Run that same span of time forward from today, rather than backward, and you land roughly at the point Oberg's models place both spacecraft's first full galactic orbit. Throughout that long galactic orbit, the two spacecraft won't travel identical paths. Both oscillate up and down relative to the flat plane of the galaxy as they orbit, the same way our own sun gently bobs above and below the galactic plane over time. But Voyager 1's oscillation is considerably more dramatic than its twins, according to Oberg's models, carrying it so far above the main disk of the galaxy that from that vantage point, it would see roughly half the density of stars we're used to seeing from Earth. That difference in trajectory turns out to matter enormously for one specific, very physical reason: dust. Here's where the Golden Record itself enters the story directly, because its survival depends almost entirely on exactly this kind of orbital detail. The record is built to last. A gold-plated copper disk, protected beneath an aluminum cover, engineered from the start with deep time in mind. But the single greatest threat to it, according to Oberg's research, isn't decay or corrosion. It's dust, specifically the vast interstellar dust clouds scattered throughout the Milky Way, through which both spacecraft will inevitably pass again and again over these immense timescales. Individual dust grains, some smaller than 1,000th of a millimeter across, strike the spacecraft at speeds of several miles per second. And even a grain that tiny leaves a small, vaporized crater on impact. Over millions and billions of years, Oberg described this as acting like a steady rain, gradually sandblasting away at the spacecraft's outer surfaces. It's worth understanding exactly what's inside that gold-plated disk, because it's a genuinely remarkable piece of engineering in its own right, independent of anything to do with dust erosion. The record contains 116 images encoded as analog data, along with greetings recorded in 55 different human languages, a curated 90-minute selection of music spanning cultures and centuries, natural sounds of Earth including wind, thunder, and animal calls, and even a recording of human brainwaves captured from a woman thinking about the history of Earth and what it means to fall in love. According to Anne Druyan, who worked alongside Carl Sagan on the project and later married him, the goal from the very beginning was to build something with a shelf life measured in hundreds of millions of years, if not longer, a genuinely deliberate design choice, not an accidental side effect of using durable materials. Because Voyager 1 spends more time above and below the crowded galactic plane, precisely where those dust clouds are thickest, Its golden record faces a specific kind of risk. Its outer unprotected surface is more likely to gradually erode over time. Voyager 2, by contrast, tends to stay closer to the plane itself, but its orbital path through the galaxy is considerably more chaotic and harder to predict with any real precision, meaning its record's fate is murkier, but for a different reason: the sheer unpredictability of exactly which environments it will eventually pass through. There's an additional wrinkle here, too. These interstellar dust clouds aren't just abrasive, they're also massive enough, in aggregate, to gravitationally tug at a spacecraft's trajectory as it passes through, occasionally bending Voyager 1 or Voyager 2 onto a meaningfully different path than originally projected, sometimes flinging them farther out into the galactic outskirts, sometimes pulling them in closer toward the crowded, dust-thick galactic core. Despite all of that accumulated risk, Oberg's modeling reached a genuinely reassuring conclusion, at least on the timescale of individual human civilizations. Both golden records are highly likely to survive at least partially intact for more than 5 billion years. That's longer than complex life has existed on Earth, and considerably longer than the Sun itself has left before it exhausts its own hydrogen fuel and swells into a red giant. It's also, not coincidentally, right around the point where the next major event in this story arrives, one that has nothing to do with either spacecraft directly and everything to do with the galaxy they're embedded in. In roughly 5 billion years, astronomers expect the Milky Way to collide with its massive neighbor, the Andromeda galaxy. According to Oberg's modeling, the collision will violently warp the Milky Way's orderly spiral structure and possibly destroy that structure entirely. Voyager 1 and Voyager 2, still drifting somewhere within the galaxy at that point, would inevitably get caught up in that merger, and predicting exactly what happens to either spacecraft during the collision itself becomes genuinely difficult, given how chaotic that kind of galactic scale event actually is. Before that collision even happens, though, each spacecraft is likely to have at least one more close-ish encounter with an individual star along the way. Though, as Oberg pointed out, that encounter is likely to involve a star system that doesn't even exist yet today, formed from gas and dust that hasn't yet collapsed into a star, somewhere in the long 5 billion year stretch between now and the merger. It's worth noting that the Milky Way Andromeda collision is itself one of the more confidently predicted events in all of long-term astronomy, rather than a speculative outlier. Astronomers have directly measured Andromeda's motion toward the Milky Way for decades, and the two galaxies are currently closing the gap between them at roughly 250,000 miles per hour. Despite the term collision, galactic mergers like this one don't actually involve many direct star-to-star impacts. The distances between individual stars, even within a single galaxy, are so vast that stars themselves rarely strike one another directly. What actually happens is a slow, gravitationally driven reshaping of both galaxies' overall structure, playing out over hundreds of millions of years, eventually settling into a single, larger, likely elliptical galaxy that some astronomers have taken to nicknaming Milkomeda. Oberg's modeling put a specific number on Voyager's odds during the collision itself. Roughly a 1 in 5 chance that the merger's chaotic gravitational churn ejects either spacecraft out of the newly combined galaxy entirely. Though, even in that scenario, the spacecraft would remain gravitationally bound to the general neighborhood, rather than being flung off into deep intergalactic space with no connection at all to its origin galaxy. If a spacecraft stays inside the merged galaxy instead, its golden record's biggest remaining threat would shift away from dust entirely, since star formation and the explosive stellar deaths that produce fresh interstellar dust are both expected to slow dramatically after the merger settles down. Instead, the primary risk becomes rarer, higher energy events, direct collisions with fast-moving cosmic rays, and the occasional stray molecule of superheated gas. Real threats, but ones that occur far less frequently than the steady dust grain rain both spacecraft currently endure inside the Milky Way today. And this is where the timeline finally stretches into the range this video's title is actually asking about. Depending on exactly how much interstellar dust survives inside the newly merged galaxy after the Andromeda collision settles down, Oberg's modeling suggests both Voyager golden records could plausibly remain at least partially intact for trillions of years, potentially, in the most favorable dust conditions, for what Oberg described as trillions of trillions of trillions of years, though he was careful to frame that outer estimate as dependent on genuinely uncertain long-term assumptions about the merged galaxy's dust content, not a confident, precise prediction. 10 trillion years specifically sits at a genuinely strange transitional moment in the wider story of the universe, based on broader cosmological research into the far future. Separate from Oberg's spacecraft-specific modeling, but directly relevant to what that far future would actually look like around Voyager 1 by that point. According to that broader body of research on cosmic timescales, 10 trillion years lands well after the Milky Way and Andromeda have fully merged into a single, larger galaxy. and deep into what astrophysicists sometimes call the tail end of the stelliferous era, the long cosmic period, expected to run up to roughly 100 trillion years, during which most of the universe's ordinary light still comes from stars undergoing nuclear fusion. By 10 trillion years, though, the universe is well past its stellar peak. Sun-like stars have long since burned out. Even the longest-lived stars in the universe, small, dim red dwarfs that burn their fuel with extraordinary efficiency, are only beginning to reach the final fading stages of their multi-trillion-year lifespans around this point, according to standard stellar physics. To put that red dwarf lifespan in perspective, the smallest, dimmest red dwarf stars are calculated to burn through their hydrogen fuel so slowly and efficiently that individual stars of this type can remain actively fusing for anywhere from 1 to 10 trillion years, depending on their exact mass, meaning the 10 trillion year mark. This video is built around lands almost precisely at the point where even the longest-lived, most fuel-efficient stars in the entire universe are just beginning to sputter out for good. Our own sun, by comparison, will have exhausted its own fuel and ended its active life a full 10,000 times sooner than that, in a comparatively brief 10 billion years. By the time Voyager 1 reaches this 10 trillion year milestone, virtually every star that was ever going to form throughout the universe's entire stellar forming history will have already lived out its full natural lifespan. Oberg's own description of this general era, drawn from his modeling of the merged galaxy's conditions, paints a fairly stark picture. A point so distant that stars have largely exhausted their fuel, and star formation has ceased almost entirely across the merged galaxy. What remains, drifting through that same volume of space as Voyager 1 and Voyager 2, would overwhelmingly be stellar remnants, black holes, white dwarfs, and neutron stars, the dense, burnt-out cores left behind after ordinary stars finish their lives, rather than the bright, actively fusing stars that fill our night sky today. According to Oberg, the only significant source of light left in that far future galaxy would come from rare supernova-like explosions, triggered not by ordinary stellar death, but by the occasional, genuinely rare collision between two of these already dead stellar remnants, events Oberg estimated might occur, on average, once every trillion years or so. He described the golden records, if they've survived that far, as potentially bearing silent witness to exactly those isolated flashes of light in an otherwise profoundly dark galaxy. It's worth spending a moment on why white dwarfs, neutron stars, and black holes specifically dominate that far future landscape, because it follows directly from ordinary, well-understood stellar physics rather than anything speculative. Every star eventually runs out of the hydrogen fuel that powers its nuclear fusion. Stars roughly the size of our sun swell up, shed their outer layers, and collapse down into a white dwarf, a dense, slowly cooling ember that, given enough time, will eventually fade into a cold, dark object sometimes called a black dwarf, though current estimates suggest that full cooling process alone takes far longer than the current age of the universe to complete. More massive stars end their lives in supernova explosions, leaving behind either a neutron star or, for the most massive stars of all, a black hole. Because these remnants, once formed, no longer generate new light through fusion the way an active star does, a universe with a high enough proportion of remnants relative to active stars naturally grows dark, almost by definition. Not because anything catastrophic happens, but simply because the ordinary process of stars living out their full natural lifespans, at galactic scale, eventually runs its course. It's worth being honest about the nature of a prediction stretching this far into the future, rather than presenting it as settled fact, because that honesty is really the whole point of taking a question like this seriously in the first place. Nobody can tell you with certainty what will happen to a specific piece of hardware 10 trillion years from now. The uncertainty compounds with every additional order of magnitude of time, and Oberg's own presentation repeatedly framed the most distant estimates as dependent on assumptions about dust density, merger outcomes, and long-term galactic evolution that remain genuinely unresolved even today. What makes this kind of forecast valuable isn't false precision. It's that the underlying physics, gravity, orbital mechanics, the statistical behavior of interstellar dust, and well-established models of how stars age and die are solid enough and well-tested enough at every timescale we actually can observe directly, that extending them forward carefully and with appropriate caveats produces a genuinely informative picture rather than pure guesswork. There's also a meaningful difference worth drawing out between two very different kinds of far future science, because this video sits closer to one side of that line than the other. Predicting stellar evolution, galactic mergers, and dust density using orbital mechanics and known nuclear physics, the kind of work Oberg's research is built on, rests on physical laws that have been tested repeatedly and rigorously, even if applying them across trillions of years naturally introduces larger error bars the further out you go. That's meaningfully different from far more speculative territory. Some cosmologists explore even further into the future. Questions like whether protons themselves eventually decay over timescales measured in numbers so large they're difficult to even write out, which would, if true, eventually break down ordinary matter entirely, gold-plated copper disk included. That kind of ultra-long-term physics remains genuinely unconfirmed and actively debated. 10 trillion years, by contrast, sits safely within the range where established stellar and galactic physics, not speculative particle theory, is doing essentially all of the predictive work. So, pulling this all the way back together, where will Voyager 1 actually be in 10 trillion years? Based on the best available modeling, it will very likely still be physically intact, still carrying its golden record, drifting somewhere inside the single merged galaxy that used to be the Milky Way and Andromeda, moving through a mostly dark, mostly dead galactic landscape, populated almost entirely by black holes and burnt-out stellar remnants, in a universe where new stars have all but stopped forming altogether. It's not a place. It's closer to a condition, a specific, physically describable state of the universe that our current understanding of physics genuinely predicts, even if no human being, and likely nothing resembling a human civilization, will ever be around to confirm it directly. There's something worth sitting with in that image specifically, beyond just the raw scale of the numbers involved. Ed Stone, who served as Voyager's project scientist for 50 straight years, from 1972 until his retirement in 2022, passed away in June 2024, having spent his entire career watching this mission repeatedly outperform every expectation anyone had for it. He never saw the spacecraft reach interstellar space's outer edge, let alone anything resembling the trillion-year timescales this video has been describing. Nobody involved with the mission ever will. And yet the calculations exist anyway, carried out not because anyone expects to verify them personally, but because the physics genuinely allows the question to be asked and meaningfully answered, which is itself a strange and specific kind of achievement, independent of whether any of us will ever know for certain how the story actually ends. If you want to dig into the actual research behind everything in this video instead of taking my word for it, all of it is drawn from Nick Oberg's presentation at the 237th meeting of the American Astronomical Society, as reported directly by Space.com, along with NASA, and JPL's own published details on the Golden Record's construction and the Voyager mission's current status. I'll leave the specific sources referenced below so you can go verify the sourcing yourself. So, a small gold-plated record built by hand in 1977 to last, at minimum, a few 100 million years, potentially drifting through a nearly starless galaxy 10 trillion years from now, having outlasted the Sun, the Milky Way's original shape, and very possibly every trace of the civilization that built it. That's not science fiction. That's a genuine, careful extrapolation of real physics, run forward, about as far as physics can currently be trusted to go, using real data from a real spacecraft that, right now, this week, is still faintly transmitting back toward the small blue planet it left behind nearly 50 years ago. Let me know in the comments what you think should happen to it. Should we hope something finds it someday? Or is the point of the whole message that it was sent at all, regardless of whether anyone's ever there to receive it? And if you want more videos digging into where real science and genuinely mind-bending timescales actually meet, subscribe. Because this is exactly the kind of question we'll keep chasing down with the same sourcing and the same honesty every time, using real published research rather than speculation dressed up as fact. Sources referenced in this script. Verify before publishing. Space.com. Scientists' predictions for the long-term future of the Voyager Golden Records will blow your mind. By Megan Bartles, originally published February 23, 2021, updated August 17, 2022. Reporting on Nick Oberg's presentation at the 237th meeting of the American Astronomical Society, Wikipedia. Voyager Golden Record entry, citing Voyager 1's projected 1. 6 light-year pass by Gliese, 445 in approximately 40,000 years. NASA, Science, Voyager mission overview pages on current spacecraft status and the Golden Record's construction. NASA.jpl. Ed Stone, former director of JPL and Voyager project scientist, dies. June 2024, on Ed Stone's 50-year role leading the Voyager mission's science team general published research on the far future of the universe and the stelliferous era timescale of ongoing star formation, referenced for broader cosmological context around the 10 trillion year mark word count of spoken narration, excluding this source list, approximately 4,500 words, verified by direct word count against the final script text above. If your platform's word counter comes in slightly different due to how it handles hyphenated terms and numbers, treat this figure as the reliable one, since it was checked directly against the delivered script text rather than estimated in advance.